Video number 3 will take us through the atomic structure and source of charge. For many of you, this will be a quick review of things you had in chemistry. In looking at this, we see that matter is made up of atoms, and generally atoms are composed of protons, neutrons, and electrons. Now today as physicists we realize that there are many other subatomic particles. Now let's break that word apart. Subatomic. Sub meaning smaller than. So there are many other particles smaller than the atom. That is, the proton, the neutron, and the electron are not the only three particles inside of the atom. But these are the three major particles that are there. The proton and the neutron, because they both reside in the nucleus, are known as nucleons. Nucleons. Electrons, however, are not found in the nucleus. They move around in this empty space known as the electron cloud. The electron cloud. Now the next slide gives us an example of what the atom does not look like. Many times people draw this to represent a picture of the atom. And it is a simple representation of an atom where we put the electrons on circular rings going around a central core. For those of you who've had chemistry, yes, this is the Bohr model of the atom, named after Niels Bohr, scientist who was given credit from this. And it took several scientists to get up to this point. You had Dalton, who came up with the idea of that there was a definite nucleus. You had Ernest Rutherford, who tested for the idea of the nucleus through his gold foil experiment. You had J.J. Thomson proving for the existence of the electrons. Beyond that, you had others getting the charges of the electrons, charges of the protons. You had ones like Chadwick, who were getting the fact that the neutrons had to be in the nucleus because they provided mass but no additional charge. So that got us to this basic structure. And if you compact this down, a lot of times this is seen as a bullseye model, a series of concentric circles, rings, if you will. And you might have learned in chemistry things like counting out from the nucleus, the names of the rings would have names such as, if the nucleus was here, sorry about that, wrong pen. If the nucleus was here, the first ring's name is K, the next ring's name is L, the next ring's name is M, the next ring's name is N, the next ring's name is O, the next ring's name is P, and the next ring's name is Q. And these would be these rings flattened down like a pancake. And we can see how many electrons would be on each of these rings by using 2n squared, where n is the ring number. So for K is 2 times 1 squared. For L, it's 2 times 2 squared. So K is 1 squared is 1 times 2 would be 2. L, 2 squared is 4 times 2 would be 8. M, 3 squared is 9 times 2 would be 18. N, 4 squared is 16 times 2 would be 32. O, 5 squared is 25 times 2 would be 50. P is 6 6 squared is 36, times 2 would be 72. And then Q is 7. 7 squared is 49, times 2 would be 98. And so this was a basic or rudimentary way of determining how many electrons could be on each ring. And so this was the work, again, of Niels Bohr. And this was the Bohr model. And this is what got us up to a lot of our work through Einstein, and as we started looking at the quantum model. And when we got ready to look at the quantum model, things needed to change. When things decided to change, it had to be then that we needed to instead look at a more complex model, and the quantum model then looked not just at levels but at sublevels. And again, for those of you who've had chemistry, you talked about the quantum numbers, the principle, the azimuthal, the magnetic, and the spin. And I could get into a whole litany with that. But you start developing a model of things that look like your principle is the S, which is a sphere, and your azimuthal can be sort of like a donut, or it can simply be so the Z, I'm sorry, this is S, this is P, this is D here. D also comes in varieties that look like flower petals, like so. And we can have another D that looks like flower petals at the other angles. This is where my poor drawing comes in. But the end story here is when you put this all together, these are the D's, and then the F's, as you may recall, is the next series of sublevels. If we start meshing these all together, if you can mentally get a picture of what it looks like to take an S here, and then we're going to take a P, and so let's put P on top of it here. And you never have one P in any case. You're going to have, if we've got a D, for example, we're going to have 3 P's. So you've got this P comes in and out of the board at you. And then one more time. And then now, quite jumbled, isn't it? Now, don't forget that in the bottom of it all, who we had there was this S. If I was a famous artist, this would be worth a wad. Now, what does this all mean? That's the shape of an atom, not the little drawing we had a moment ago. Notice you can sort of get the highlight here of the S cloud, trace around. But then you've got the humps of the P's and the D's as they go around there. So moral of the story is, folks, an atom doesn't have one definite nice little package shape, okay? It's not some simple thing that we just draw and we are done with it, okay? That's not the case at all. Not the case at all. All right, so this also tells us that the atom is much more complex, because in addition to just those three particles, if the electrons can behave in such a complex way, when we got looking at the nucleus, it was much more complex. So number one, there's more particles than just protons and neutrons inside the nucleus. There's all sorts of things: baryons, mesons, leptons, kaons, pions. And then things like protons and neutrons are made up of even smaller particles called quarks. Okay? And you'll hear this word, You'll hear this word here, that things are made up of quarks. Okay, and quarks are the particles that make up protons and neutrons. And it's basically, that is the difference between a proton and a neutron. That's the reason why protons have a positive charge and neutrons have no charge. They're both basically the same mass, 1.673 versus 1.675 times 10 to the negative 28. It's a matter of the type of quark and which way the quark is acting as to what's going on with it from there. Now, the electron, on the other hand, is much, much smaller. It's 9.109 times 10 to the negative 31st. Times 10 to the negative 31st is 1,000 times smaller than the protons or neutrons are. Okay? 1,000 times smaller. So, moving on. So, all right, so looking at the charge here, this goes back to Ben Franklin. Sure you all remember here, neutrons are neutral, protons are positive. Remember, NNPP. NN, neutrons neutral, protons positive. NNPP. So that means the electrons are negative. It is the movement of electrons or flow of electrons that generate electricity. Movement of electrons make electricity. Okay? Electrons make electricity. Atoms want to be neutral. In order to be neutral, they have to have an equal number of protons and electrons. Let me say that again. In order to be neutral, they have to have the same number of protons and electrons. Number of neutrons does not matter because they're neutral. If an atom gains electrons, then it is said to have a negative charge, and it's called a negative ion. If it loses electrons, it has a positive charge, and it's called a positive ion. Now, what does that mean? If it's a negative ion, that means it has more electrons than it does protons. If it has a positive charge, then it has more protons than it does electrons. Now, as we talked about a few minutes ago, the mass of the protons and neutrons are much more massive than the electrons. Okay? And so that's one reason why, when we're talking about who's really going to have a chance to move between the three particles, it is the electrons who are easier to move because they're that much lighter. They're lighter. Okay, so generally our nuclei don't move, it's the electrons that are moving. Okay. Now, a couple of things are conserved in physics. Energy is conserved. We can't make energy, we can't destroy energy. Momentum is conserved. Charge is conserved. Meaning you can't create it, you can't destroy it. Another thing about charge is opposite charges attract, like charges repel. You put a positive and a negative together, they're going to want to stick to each other. You put two positives or two negatives together, they want to fly away from each other. And the last thing is, even though there's a great big difference in mass between the proton and the electron, because the difference in charge between the proton and the electron is just a matter of +1 and -1, they are attracted to each other perfectly. Perfectly. The electron is said to have a charge of -E, and the proton has a charge of +E. Now the symbol for the proton is a P positive. P as in Paul, positive. But when we talk about in terms of charge, we value everything in terms of the letter E for electron or electricity. Now, the next little bit here I'm going to skim through because a lot of this you can read through this history. The electron was discovered by J.J. Thomson. Robert Millikan, he's there on the right. J.J. Thomson he did the work with the cathode ray tube. Robert Millikan does the charge of E by doing his famous oil drop experiment. Okay. They get the value of the charge of an electron to be 1.602 times 10 to the -19th coulombs. Let's all say that, please. Coulombs. Cou, like a baby goes, coulombs. Coulombs. Good job. 1.602 times 10 to the -19th coulombs. Now, of course, we're naming this after scientist Coulomb for his work with charge there with that. Okay. Let's take a look at this question here. An atom in its normal non-ionic state, meaning not positive or negative, has no charge. This is due to the fact that atoms, A, have only neutrons, B, have no protons or electrons, C, have equal numbers of protons and electrons, D, have equal number of protons and neutrons, or E, you need my help. Take a moment and pause the video now. Did you pick answer choice C, have equal numbers of protons and electrons? That is why an atom has no charge. They have equal numbers of protons and electrons. Good job. Which object moves freely within the entire atom? A, the electron. B, the neutron. C, sorry about that. Try this again. A, the electron, B, the neutron, C, the proton, D, the nucleus, or E, you need a little bit of help. Which one do you think moves freely throughout the atom? And I hope you all said A, the electron. Number 6, an atom is composed of A, central nucleus that is surrounded by neutrons, B, an uneven distribution of electrons and protons in a spherical shape, C, a central nucleus surrounded by electrons, D, a central nucleus containing protons and electrons, or E, again, you need my help. Take a moment and make your selection there, please. Did you select C? It is a central nucleus surrounded by electrons, because both the proton and the neutron are found in the nucleus. Good job. This is where this part of the presentation is going to stop at. The next part will go into solids, which is going to be then talking about conductors and insulators. You're now ready to complete assignment number 1, daily quiz 1 on electrostatics. Good luck.